We will have a good and great session, and welcome everyone in the second World Conference for products for date palm fibers and for palm trees. And welcome our speakers and our participants today. And I hope you all will enjoy the presentations. And we will start with our speaker, Dr. Mohd Fadzli Ismail. And he spoke today about the experimental performance evaluation of Arenga Pinnata reinforced Nanosilica modified epoxy composite loaded in compression. Let's welcome Dr. Ismail. And Dr. Ismail, the floor is yours. Would you unmute yourself, please? Thank you.
Sorry. Sorry, I have problem to share my screen. Wait a minute.
Yeah, no problem.
If you need any technical help, please let us know.
Okay, perfect. You may start.
Assalamualaikum and a very good afternoon to everyone. I'm Mohd Fadzli bin Ismail. Now I'm going to present my research paper entitled Experimental Performance Evaluation of Arenga Pinnata Reinforced Nanosilica Modified Epoxy Composite Loaded in Compression. So this is the my presentation outline. I will start brief the introduction, methodology, result and discussion, and lastly the conclusion. So this result focus on the effect of nanosilica on the compressive properties of epoxy and also APREC. Next, fiber reinforced polymer, or also known as FRP composites, composite material made of fiber with polymer metric reinforcement. So fibers can be divided into synthetic fibers such as glass, carbon, and Kevlar, and natural fibers such as cotton, jute, hemp, knaf, and sisal. So for FRP can be in various forms such as random, discontinuous, unidirectional, bidirectional, woven, and etc. In this study, we are focusing on the unidirectional because its properties can be used for other investigation and evaluation. So nowadays, natural fibers has been used to replace the synthetic fibers because its advantages such as natural availability with abundance of resources all around the world that lead to low cost. It is also environmentally safe due to their biodegradability nature, less harm to human body compared to synthetic fibers such as glass fiber. Besides, it is also good mechanical properties and low density. So in this research, we are using Arenga Pinnata fiber or sugar in Indonesia. Arenga Pinnata is one of the plants that produce black color fiber all around it is also a fast-growing plant which about 10 years here, such as Indonesia and Malaysia. So Arenga Pinnata fibers has its specific advantages to extract the fiber from its sources because it is located outside the trunk, and it is also high durability and good resistant to seawater. This is the application of Arenga Pinnata. We can use as a rope, a broom, roof, and boat. It also can be sold in a large scale in Indonesia. Due to its resistant to seawater property, Arenga Pinnata reinforced epoxy composite or APREC can be used as replacement of bridge and pathway in seawater. Bridge and pathway of wood need to be maintained quickly. We need to put to and we need to replace the tank every 2 to 10 years. Incorporate of constituent material. Composite can be classified according to shape and dimensions of nanofillers. Here, there are 3 types of nanofillers. We have 1-dimensional, 2-dimensional, and 3-dimensional nanofillers. So the objective of this project is to evaluate stress strain response and properties of Arenga Pinnata fiber reinforced epoxy composite, or we call it as APREC. So this is the material which Arenga fibers. Second is epoxy resin, and third is nanosilica. So Arenga Pinnata fibers was harvested from Kuala Pilah, Negeri Sembilan, Malaysia. And epoxy resin, we use Miracus 1517, which is consists of part A, which is the epoxy resin, and part B, which is the hardener. The ratio of the epoxy and hardener used was 100/30. Next is nanosilica nanopox. We use nanopox F400. Nanopox F400 in the form of spherical shape with the mean size of 20 Newton meter, and we dilute the nanopox into 3 different weight percentages of nanosilica, which are 5 weight percent, 13 weight percent, and 25 weight percent. So this is the methods used in the to produce the specimen. The first is we use 25 volume fraction of Arenga Pinnata fiber content because this is the optimum volume fraction that we use to what we call it 25 volume fraction is the optimum get the optimum result for the mechanical properties. And then we have 3 different weight percentages of nanosilica incorporated in the epoxy. So first we mix the epoxy resin with nanosilica by using magnetic stirrer. A magnetic stirrer machine that was set to 400 RPM and 80 degrees C for 1 hour. Then we place the mixture inside a vacuum oven with a pressure of 0.07 megapascal for 1 hour. The function is to remove the air bubble. Next, we mix the mixture with hardener before pouring into the mold that containing Arenga Pinnata fibers. Then the APREC was made using hand layup method with a rectangular shape mold. And then finally, the specimen were pressed for 24 hours using cold press machine for curing process. And then this is all the specimens fabricated in this project. We have pure epoxy, nano-modified epoxy, And then this is pure APREC, unidirectional APREC. And this is nano-modified unidirectional APREC. This is the compression setup for this experiment. This is the sample of the experiment in the Mohd. We use rectangular shape specimen with dimension of 100 mm in length, 10 millimeters in width, and 4 millimeters in thickness, according to the ASTM standard. And then this is the result. This is the effect of nanosilica on the compressive stress strain curve of epoxy and APREC. So this is the graph for epoxy, and then this is the graph for APREC. As can be seen in figure A, the specimen with 25% weight of nanosilica had the highest slope gradient, represented by the purple color, and then followed by the specimen with 13% weight of nanosilica, and also followed by the 5% weight of nanosilica. And then the yellow line is the pure epoxy, shows the lowest curve. And then, however, the pure epoxy specimen shows the highest compressive strain, before failure, and then followed by the specimen with low weight percentage to the higher weight percentage. While for APREC, as can be seen, all specimens which were incorporated with nanosilica had better resistance to compressive load compared to specimen APREC during the 0 to 5% of compressive strain. And then after that, the specimen with 25% weight, 13% weight of nanosilica curve started to drop below the specimen of pure APREC. Specimen with 5% weight maintain the highest slope gradient of the curve from the start until the failure.
Dr. Ismail, please try to wrap up in like 3 or 5 minutes.
Okay. Next, the effect of nanosilica on the compressive modulus of epoxy and APREC. As can be seen, this is for epoxy, and then this is for APREC. As can be seen, the result of the compressive modulus of the specimen with nano modified greater than the pure epoxy. And then for APREC, the compressive modulus of the specimen with nanosilica was higher than the pure APREC, but we have the highest in 5% weight of nanosilica, but it dropped when we added more weight percent of nanosilica. This is occur due to the this current formulation. The FRP composite became improper weighting that has been present by my colleagues before this because of the reduction of epoxy content in the composite. And then this is the result of the effect of the nanosilica on the compressive strength and strain of epoxy and APREC. As you can see, the addition of 5, 13, and 25% of nanosilica into the epoxy increase the compressive strength of the epoxy, and then the addition of the 5% of nanosilica into the APREC improve the value of compressive strength of APREC. However, the value dropped if we add 13 and 25% of nanosilica. So as a result, the strength of the epoxy was improved by the addition of the nanosilica content from 5 to 25, and then the strength of the epoxy also improved the strength of the APREC until 5%. However, this reduced due to the interfacial bond of APREC. This is for 5% of APREC, and then this is for 25% of APREC. As you can see that the Arenga Pinnata fiber detached from the epoxy matrix because the fiber still in good condition after the compression test. And then this is to the second image, evaluated to identify why the composite has the lower strength compared to the 5%. This is as you can see that the epoxy matrix burst out after the test. This means that the compared to the 5% and without nanosilica specimen, the epoxy became more brittle. Besides, the Arenga Pinnata fibers also seems detached from the epoxy matrix, showing that lack of interfacial interaction between fiber and also epoxy matrix. As a conclusion, the addition of 5% of nanosilica content of APREC result the greatest improvement of the strength. However, it reduced after we increase the percent of weight percent of nanosilica. This is due to the improper weighting in the composite. So for future works, we will study the new formulation to overcome improper weighting issue that has been highlighted, and then thus increase the properties, strength properties of APREC when adding more than 5% of nanosilica. So that's all. Thank you.